Now let me introduce you our first speaker, somebody that I respect, that I know, I have to confess that I know for more than 20 years. And I was always impressed by his creativity, his technical skills in many areas, and his leadership. Thank you so much, Nick, for being today with us. Nick has over 30 years of engineering and management experience and has created and managed large teams focused on the development, mass production, and marketing of the semiconductor products globally. Right? Before founding Brite Solar Technologies, he was the managing director for channel development in Europe, Africa, Middle East for the solar business unit of Applied Materials. In addition, previously, he was division director at Atmer, where really I met Nick for the first time after he sold his company, his startup data communication technologies to Atmer. And also he was the director of the Integrated Electronics Group at RTI International, one of the largest independent research center in the US for over 10 years. He served as a professor at the Duke University. He was the manager of Integrated Electronics Department at Research Triangle Institute and has been a special advisor to the Ministry of Macedonia and Thrace in Greece for matters of technology. I know it's long, but I wanted to share with you this impressive biography. He has one book. I recommend you know that really you search, and over 100 papers in journals and conferences proceedings, and has also US patent. In addition, he is a member of several international trade and scientific organizations. Nick will present us today technology for sustainable food production with a positive environmental impact. Nick, thank you so much again. It's really an honor today to have you with us. Nick, the stage is yours.
Thank you, Hani. It's great to know you all this time, and good morning to everybody. And let me share my screen. Okay.
Yes.
Okay. What I would like to discuss and present to you today is technology for sustainable food production with a positive environmental impact. Internationally, we have this water, energy, and food nexus. And because until 2030, energy has to increase by 50% in order to support increase by 50% of food supply in order to support the increasing world population, which is estimated to be 9.7 billion by 2050. And then that puts a lot of pressure on water demand, which needs to increase by 30% by 2030. And if you see the global sum of withdrawals, you see that agriculture withdraws 70% of water globally every year. And of course, if we increase that by 30%, then there's not going to be any water for people to drink. The effect of climate change on agriculture is you have higher temperatures, which shift in region and crop viability. It's too hot in many regions in order to cultivate crops. Because of the temperature, you have increased irrigation yields, needs. And of course, one very important thing is that the bee population declines, and therefore crop pollination becomes a problem. We have longer growing seasons, more extreme weather, which causes crop damage, and then the water supply variability. Farming has always been a risky business, but now with the climate change, it becomes riskier while the needs for food production increase. You already see it in 2021, French wine ravaged by devastating frost. These are some of front page announcements in the press that relate to adverse weather and agriculture. The solution to this problem is controlled environment agriculture, which is coming in two versions. One is greenhouse farming, which offers a complete control over environmental conditions in terms of light, temperature, humidity, and CO2 supply. And it has been proven that high-tech greenhouses yield 10 times the yield of farming in open field, while using 1/10 of the water, and offer, of course, complete protection of the crops. And then the other one is crop coverings, or what we call agri-PV, which we put a covering over the crops in order to protect them from birds, hail, wind, frost, heat. There is precision watering because of that shading. And that, on the average, offers a 20% yield increase at 20% less water use. But benefits come with the price, and the price is increased energy use, which in the case of greenhouses is 10 times more. In terms of agrivoltaics, we have an integration of PV into a controlled environment architecture, while in solar greenhouses, the roof of the greenhouse is replaced with solar panels, but not any type of solar panels, but transparent solar panels, because you need the crops to grow underneath. So the Brite solution on this is a semi-transparent solar panel, which produces energy, comes in different sizes and in different transparencies, so the transparency of the panel adapts to the light requirements of the crops, and at the same time, it covers the structure. The panel has a nanostructure coating material which absorbs UV light and retransmits it in the red region of the spectrum where the plants photosynthesize. So this depiction of the functioning of this material, we have a coated glass and UV lamps behind it. And then when the UV lamp comes on, the glass becomes red because it absorbs all the UV light and retransmits it in the red region of the spectrum. The UV light, of course, is useless for both crops and solar cells. However, the red light can be used by both, by plants in order to increase the yield, and by the solar cells in order to increase the cell efficiency. Uniform shading, critical to uniform plant growth. You see on the right here a science fair project where essentially a plant will always follow the light. And if somebody is trying to use conventional PV panels over a greenhouse structure, like this picture here, then of course the shading is non-uniform, and therefore under the intense shade the plants will not grow, while in our technology the shading is very uniform over the entire area of the greenhouse, and the plants grow uniformly without any yield impact. In terms of agri-PV, the current technology is here on the right, using conventional solar panels. And of course, this technology can be used only if you have grass and animals grazing under that. However, if you are cultivating food, then you have to provide a uniform light environment for that. And this is our technology, which has been installed over several types of fruits. This is a picture from an installation over blueberries in Holland. And what we do here is the structure installs the panels at an angle. We collect the rainwater, and through this gutter, we take it through the vertical pipe to a central pipe that collects and stores the water. So we offer water management and complete protection of the plants from adverse weather conditions, and solar energy production. Actually, agrivoltaics, this is needed by everybody, by government, because it reduces disaster payments to the farmers, by the farmers because they protect their crops, and therefore they have a very deterministic production every year. They have a second revenue stream because they also produce and sell energy in addition to crops, and then increase yields for their crops, and therefore increase profit. And of course, everybody needs it because there is a healthy produce and at reasonable prices, because of the production of the crops, and then decrease reliance on fossil fuels, and therefore reduce CO2 footprint per kilogram of product produced. In fact, in a pilot greenhouse we built over a vineyard in Greece, we reported for the first time in agriculture a negative CO2 footprint per kilogram of grapes produced. That's 15.78 kilograms minus 15.78 kilograms of CO2 per kilogram of grapes produced. And this is a significant result. In terms of agri-PV, we did a study where we essentially studied the impact of the technology on the yield of blueberries. And these are different varieties of blueberries under a canopy of transparent solar panels with different transparency levels. We found out that in general, under 40% transparent panels, the blueberries did better than less transparent panels and compared to the open field. And this is without any disaster happening. 2 kilometers from our installation, there was another farmer with blueberries in the open field, and that lost 65% of his crops because of a hailstorm. This is an installation in the Netherlands. There are agri-PV additional incentives offered in different parts of the world. In Europe, agricultural land cannot be used for photovoltaics. That's fertile land, and therefore there's a large piece of land that now can be used for photovoltaics and agriculture at the same time. In Japan, it's the same thing. In the US, there is the SMART program in Massachusetts and now in New Jersey, where the PPA has a premium of 6 cents per kilowatt hour for dual use of land. And I want to leave you with a dramatic potential impact in crop protection and dual use of agriculture and photovoltaics. Let's take the grape cultivation in Europe. That's 3.134 million hectares. To make it dramatic, let's assume that 50% of that is using agri-PV in order to protect the crops. That will be equivalent to an energy production of 720 gigawatt hours per year and a CO2 emission avoidance of 166 million tons per year. And the energy sales from the produced energy, assuming a very low 5 cents per kilowatt hour, will be 38 billion. So this is a technology that has a high potential to affect positively the production of agricultural products and at the same time decarbonize agriculture by using solar energy in order to support the energy needs for running farms. And this is very important because agriculture right now consumes 14% of energy globally per year. Thank you, and happy to be part of this conference.
Thank you, Nick. Thank you so much. And always a great gentleman, respecting time, respecting everybody. Thank you. I have 2 questions for you, Nick. The first, what are the barriers? Means the technology looks fantastic. The numbers are here. What are the barriers to adopt such kind of technologies?
The barriers for the user or the barriers for us?
I guess for I mean, why this technology? I guess I don't know exactly, but I guess that the question is why this technology is not yet wide deployed. What are the challenges to make this technology available for you, but also when you are a user, what are the challenges? I guess this is the meaning.
Okay. First of all, this product came out in the beginning of this year. We have a pilot projects done. People have been trying to install regular PV panels over farms, but because of the complete darkness of the panel, that didn't work very well for the farmer. Therefore, the need for transparent solar panels came, and we introduced this product. And there is a let's say complication for the product production in deploying this product, because different plants require different amounts of light. Therefore, every product has to have different transparency for every plant category and the geography where the product is deployed. That requires a flexibility in the panel production line that doesn't exist in production lines of regular PV panels. We are working right now with an OEM manufacturer in China, and we have limited flexibility, and we supply the product for certain plant categories. But we are in the process of completing our Series A funding for building a production line here in Greece, where we have complete flexibility to supply any products, any panel size, and any panel transparency. Because in a sense, when you deploy this product, the deployment is custom to the plant under the canopy.
Fully understood. Thank you for the answer. And I have another question. What are the next milestones of Brite technology, Brite Solar?
Yeah, the next milestones is building a factory in Greece and ramping up to more than 1.5 million square meters of panels of different transparency and for different crops and markets by the end of 23.